First of all credit this really goes to Bob, since this is largely his presentation here, and I'm here just essentially to provide some context. And first of all, I want to give my thanks to Jean-Baptiste for his presentation and his perspective, because it's focused on the importance of the designer, and it doesn't matter what the tools are in the end, it's what you do with them. And so when he talks about how solving problems is the lowest form of design, what we're going to talk about here today is how the engineering can help alleviate some of the problem solving for the designer, so the designer can focus on the things that really matter. And if we look at the history of tools that we've used to make letter forms and how they've changed over time, there's a continuing evolution. And with each new step, we've generally gotten more capabilities in some respects, but at certain times we actually lost some quality. You know, when we went from the days of hot metal, where we were cutting typefaces, optical sizes, and then we made that switch to photo, we lost a lot. And so we started realizing, oh, we can just scale a single outline, and we can use that, or we can scale a photo master to any size, and it just works, right? And we lost something when we did that. And so we're now at a place where we have even more power, and it's all a question of what we do with that power. So we have the situation here at MonoType, which may seem unique. So I think it's no secret here that we're the evolution of the bringing together of multiple companies with long histories. And so we have a large library of typefaces coming from different studios and different tools and processes. And some of the artwork goes back to the pencil drawings that were done at Linotype and Monotype that were then used to draw patterns, to cut patterns and engrave matrices and create punches and sell matrices and machines to produce typefaces with. So, but moving forward, we have this huge collection of digital data that we have in an active library that we sell actively. Now, one of the things as the new director of the studio here, I want my type designers to be able to be using these tools in ways that really serve our customers and create new opportunities for design. But if, from a market standpoint, we have to provide a lot of typefaces that are well known in this new format, I sure don't want very talented designers spending their time fixing curves and point harmonizing so that they can then get this data in a variable format. And so that's why we rely on really intelligent engineers. And Monotype has a bunch, and they report to Bob. And so I introduced Bob Taylor, who I've worked with for several years now, and whose team has working on solving the technical problems so the designers can focus on the design problems. Bob.
Thank you. Ooh. Let me switch this up and try to go directly. Let's see if is that going to work? Yeah, that's better. Okay. So, thank you. So I'm going to have a very technical talk because I'm a technical kind of guy, and so bear with me. But the real question that was posed to me and my group was, okay, variable fonts, when can we get them? How many can we have? And what is it going to cost? And so I don't know. So we had to look at it. So we've actually developed some tools working with our partners, and since the OpenType spec has come out, we've developed some tools based on the spec, and and we've done some experiments, and to date we have produced a total of 25 variable fonts of one sort or another. Now, we've only released a couple as a demo, but and most of these are just tests of the software and tests of the process and so on. So they're not production ready. So we're learning a lot, and what we're learning is that, okay, first of all, there's lots of ways to mess up fonts, and we don't want to do that. So quality cannot be compromised. So we want to make sure that if we're going to produce a variable font from one of these legacy families, that we respect the design, that any intermediate interpolations are good and usable, and that the quality is as good as we can possibly make it. Okay, so the other factors then are scope. How many axes are we going to have? What level of, what is the range of the axes and so on. That determines sort of the scope. The schedule is really about people. We can assign font engineers to this, and it's really a staffing thing. The big thing is the cost. What is the cost of this process? And cost is, so we have a production workflow in mind where we have an assessment phase, we have a preparation phase, and then we go through the process of creating the variable font. So we've scoped out what we think our workflow is going to be, and so the different aspects of this workflow are going to determine the cost, and that's going to determine how many variable fonts we're going to have in the end. So part of the assessment phase is really determining the scope. And as part of this assessment phase is what is the value of the product that we're generating. And it depends upon the importance of the family. How much does this particular family sell? And what is the business need? Do we want to do this for our main top sellers, or do we want to do it for everything in the inventory? And so a lot of the value determines the scope and the importance and the priority that we're going to assign to creating a variable font. And then beyond that, it's the level of effort. How much work is required? And one of the first things, the problems we have is locating the appropriate data. Not everything is in source format, unfortunately. So some of this legacy data is really only in binary format. And so the workflow I'm going to describe is one that we're really focused on working with binary data. And then the family design, the style, and the topology differences between the different family members will determine how much effort is involved. The character set, compatibility. In some cases, some family members have been built out for a very large character set. Other family members don't have as large of a character set. So do you cut the one down to a minimum set, or do you expand out the character set for those that are lacking? Obviously, if the family is very important, you might want to take the effort of expanding that character set. In a lot of cases, what you're going to do is you're going to compact down to the minimum character set that's common among all the family members. And then how many design axes are we going to have? And then what is the range of those axes? That's going to be determined by what's available. Typically, when we're talking about legacy families, we're really talking about weight and width and perhaps italic. We're not talking about, in very few cases we have optical size. We could create an optical scaling axis, but in most cases we're talking weight, width, and perhaps italic. So this assessment phase really involves business people, it involves typographers and our design staff, and it requires a skill set, a sense of typography, as well as some business knowledge. But once that assessment phase has been decided, then we start the whole process of creating a variable font from this legacy family. And the first step we have is what we call a preflight, and I'm sure all of you have lots of preflight steps, but the first thing we do then in evaluating the legacy family is determine the minimum set of common glyphs using the glyph name, and then we'll subset down to that common set of glyphs. Now, as part of the assessment phase, if we've added characters, that work has already been done as sort of a preparation work for here. So here we're just going to take the font data and get it ready for making it point compatible across the family members. So this is really a fully automated process of checking the glyph names, putting the glyphs in the same order, and then also checking for the compositing structure. And everything I'm talking about today is based on TrueType variable fonts. We haven't done anything with CFF2 yet. Okay. So in the TrueType format, you can have simple glyphs, you can have composite glyphs, and if a glyph is a composite, say in the regular, but it's a flat, simple glyph in one of the other family members, then you have to make a decision. Those have to be made compatible. And so you can either go back and recomposite the family member, the style that's not composite, or this process will automatically flatten or make the glyph simple across all of them. But that's another decision that impacts how much effort goes into this process. And one of the main advantages of the TrueType format is this ability to include composites and reduce the overall size of the variable font. So as much as possible, we want to try to retain that composite structure across all of the family members so that the variable font that gets produced will then have composites. So in many cases, if the font family is valuable and is worth it, we'll go back and recomposite those family members that don't have the composites. And then all of this is really getting the fonts ready for the next step in the process, which is converting the fonts to a point-compatible form. In order to make a variable font, and I'll go into this in a fair amount of detail, you actually have to have point compatibility between them. So that's a big cost driver because that can be a complex process, and it could involve manual effort, or what we're trying to do is see if we can fully automate that. And then, of course, once you have a variable font, how do you verify the quality of the variable font? We know how we have a process that's fairly extensive for doing QA on any font that we release. And so in addition to that, though, the variable nature of a variable font means that there's a lot of extra things we have to check in order to let this font go out the door. So whether or not this can be these two steps can be fully automated is going to be a big driver in the cost, and that's one of the things that we've been looking at, and that's really what I'm going to talk about today. So I'm one of those people that came to fonts from a technical background. Yes, I was educated as a physicist, so it's odd that how many people come from a physics background and wind up working with fonts, but yeah, I'm one of those people. And when I first heard about variable fonts, I was very excited, and I thought, this is a great idea. And yes, I'm approaching it from, oh, isn't it cool? We can do the slider demo and see how these things change. And but I do think that creating a high-quality variable font and putting it in the designer's hand is going to give them the freedom to do things that, if we do it right, there'll be a lot of freedom at the end. So what we're trying to do is get all the technical stuff done up front and then produce a variable font that just works. But So my dream was, yeah, font families go in, variable fonts come out, and it's fully automated. You press a button, and it just works. Well, no. So if you've ever tried to do an algorithm that works with font data, one of the things you quickly realize is that fonts are very mathematical. They use fonts, Bezier curves, and so on, but fonts are not ruled by math. They are a creative endeavor created by design people that put a lot of effort into creating just the perfect design, and there's a lot of little things about fonts that make it difficult to create algorithms for them. So one of these issues that we've been facing in terms of the cost of how to produce these fonts is point compatibility. So in order to create a variable font, you have to have, typically you'll have a regular weight, which is the default font, and then you have axes, right? And so in order to create an axis, you have to have a font that is at the end point of each axis. Okay, so I have a regular, say, and I have a bold, and I have a thin or a light. That can form a weight axis. And then if I have, say, a regular and a condensed and an extended, I can form a width axis. But in order to create these axes and to create a variable font, I have to have fonts along the different axes. And those fonts have to be point compatible. And point compatibility basically means that I have a one-to-one mapping between every point in the default font and every point in each family member on each end of the axis. Okay? So they have to have the same number of contours, they have to have the same number of points, they have to be in the same order, and so on. So, and that's illustrated on the right-hand side here, where I'm showing really two outlines. I'm showing a thin and a bold outline. And the lines show that's the line of interpolation between the two. So the control points are going to move along those lines as you change your infamous slider. And I am in the slider camp. I freely admit that. But to me, the slider is just a paradigm for the ability to create any sort of intermediate instance. And so it's really about micro-tuning or micro variations within the family. And those variations occur along these lines that are shown there. So the process of Glyphs app and FontLab and some of these other tools do a great job of making interpolatable sources once you have source data. And then you define the font in that format, and everything is built to be interpolatable through multiple masters or variable fonts and so on. What we're really talking about, though, are fonts that were never designed to be interpolated. And that's really the challenge that we're coming up with here. So beyond point compatibility, however, we came up with a term for what we really want, and that's harmony. So I'm going to talk about harmonization and making fonts, harmonizing fonts. So long time ago, 1973, before many of you were born, Elton John came up with a song about harmony. It's one of the few songs about harmony. And it says, "Harmony, gee, I really love you, and I want to love you forever." So we've been spending a lot of time lately trying to achieve harmony. So what does harmonization mean? So to harmonize a font family really means that we want to make it point compatible, but we want to do so in a way that minimizes the number of points. We don't want to add a lot of points to the design because that increases the font size. We want to have all of the intermediate interpolations be nice and reasonable and good. And you'll see some examples. I'm going to show you the good, the bad, and the really ugly. So we've produced some ugly stuff in our process of testing things. So So harmony means that there's no kinks in the outline, there's no discontinuities introduced, there's no twisting. And if you look at the interpolation between the two, it makes sense, it's reasonable, it's at least consistent with the design, the intent of the design. And that's really what harmony means to us when we talk about variable fonts. So, and it often means that we have to reflow the outline so that the original points in the default font are not the same after harmonization. So it does involve an approximation. Some people think that approximation is terrible and you should never ever do it. But unfortunately, with variable fonts, it is a requirement at times. And so we try to have an approximation method that works as well as possible and is faithful. And that's really what my team is trying to do, is we're trying to be faithful to the design, but also produce a variable font that works. So I said that fonts use math, but they're not ruled by it. And so with variable fonts, we're really talking about the mathematical field of topology. So in topology, what you do is you have a set of points, and you convert from one shape to another shape in some manner, okay? And the classic example of topology is you can take a toroid or a donut and you can convert it into a coffee cup. And to a mathematician, those two are the same, right? But that's a little bit extreme for us. What we're trying to do, however, is take a set of points in one weight, say, and transform that across the design space to, say, from light to bold. And we're doing that by manipulating the control points within the outline. Okay, but so a lot of what we're doing here is loosely based on topology. And topology tells you, however, that you cannot convert things that have, say, one hole into things that have two holes. That's just mathematically, it's not possible. Typographically, it's not possible. So, for example, we have two families, one called between one and one called between two. And you can see, for example, that the G's have a different topology or a different number of contours. One has one hole, the other has two holes. So it's not possible to interpolate between those two. So that's one thing you come up with. Another thing it's kind of interesting, is can you interpolate between two different styles? And I have a little, there we go. Okay. So yes, mathematically, it is possible to interpolate between those two. Okay? Yeah, that's not harmonious. All right? That we would not call this harmonious, and we would never ship anything like this. Okay? But it is a nice test of our algorithm to say, okay, can we make these two shapes compatible? Well, yeah, we have a very clever algorithm to do that, and we can do it, but you shouldn't do that. Okay? Another example, a little bit less, so is, can I go from one style to another style of the foot on the A? Yes, you can do that. Are those intermediate interpolations reasonable? No. We would not ship something like this, okay? So hopefully that will give you some comfort, but yeah, but at least the process works. It's a good test for the software, but it's not something we would do. So part of the assessment phase is looking at the design and saying, okay, does it make sense to do this, right? Yeah, technically we can do it, but do we really want to do that? Another issue that we face that involves topology involves CJK. So here we have two weights of a Chinese glyph, light or thin on the left, bold on the right, And typically what we do as part of our process is we remove the overlaps, okay? When you do that, however, you've made them incompatible. You can't interpolate between those two. So one of the things we've learned is that you have to preserve those overlaps. And the resulting variable font will have overlaps in it. It's not a big deal. A lot of fonts have overlaps in them, but in order to be able to do a variation you have to have the same number of contours, and you have to have that one-to-one mapping between the contours. So that's an issue. And a lot of times, if you have source data that has the overlaps removed, or binary data, you've got to go find the source data that it actually had before they removed the overlaps. So that's a consideration. So how do we plan to deal with topology differences? So there's two ways, basically. One is that you can change the design. Okay. So, and this often happens with the dollar sign. The dollar sign on the left up there is made up of 3 contours. And typically, as you go towards the bold or the heavyweight, it's really not possible or not desirable to have a dollar sign with the bar going all the way through the middle. And so you typically want this design down at the bottom here. But another way to do this is shown at the top. You could actually make them have the same number of contours by actually breaking up the bar as shown on the top right there. So that's one way, and that may or may not be desirable, but as part of the assessment phase, you need to look at some of these characters and say, how much work is it going to be for somebody to go back and redesign this? And then also, is it really desirable? In a lot of cases, it's probably not desirable. So the other way to deal with topology differences is to actually use the G-sub method, which can do a contextual substitution based upon a particular axis range. Okay, so as you're moving from left to right with the dollar sign, it gets more and more bold. At some point, in this case between the bold and the heavy, you're going to make a contextual substitution from one to the other. And I know there's been some discussion about, are people really comfortable with OpenType, but I think we've come a long way in terms of the OpenType implementations, and this is less of a problem. But in this case, the variable font would actually switch from one design to another design at a certain point along that weight axis. So here's an example where it does that. And this is actually, we're going to vary the weight as using our dreaded slider. And then we have 2 axes, weight and italic. And what you'll see is we're actually making a contextual substitution between the 2 forms of the G, and then we can go on and continue to vary along that italic axis. And you're going to get regular, a little more italic, a little more italic. So I'm going to propose an alternative to this in the end. But what this does is it illustrates that the use of the contextual substitution to go between one type of G to another type of G. Okay. So I'd like to talk a little bit about the harmonization process that at least as we've experienced it, and what some of the difficulties are. Currently, we have a process. It's a command line process that only an engineer would love, but it is fast. I can take a family of a Latin family, and I can harmonize it in about 2 seconds. Okay, and if it really has to struggle, it takes 10 seconds. Okay, from a cost perspective, there's no cost. I just run this command line, and 2 seconds later, I have a set of fonts that I can then create a variable font from. Okay, So that's great. That was my dream. It doesn't always work, though. It works about 95% of the time in most cases. So it's that last 5% that really determines the cost. But I thought I would describe the process. I think it's would be the same for anybody doing this sort of thing. The first step in harmonizing a set of a glyph or a set of glyphs in a family is to make sure that the contours are all in the same order. In other words, on the left-hand side, you can see that the green contour in the middle there is different, in a different order than the yellow. The coloring indicates what order they're in. So on the left-hand side, they're in a different order. On the right-hand side, we've reordered the contours so that the green contour is the same across all the family members, the red is the same, the blue is the same, and the yellow is the same. And we were actually developing a tool like this that uses color coding to indicate what the contour ordering is. Also, finding the start point, the point at which the contour starts, can vary across the family members. That's shown on the left-hand side. The contour at the top, they all start at the same starting point, but the other two contours start at different points. So it's non-trivial to actually find out and go around the contour and find out where it should start and then make a common starting point. But that's really required in order to have harmony, okay? So we have a process that does this. It works almost all the time. We have another process, and a step in the process, that finds extrema points. And what we need to do is we need to divide the outline up into a set of sections. Okay, and the sections are shown on the right-hand side with color coding. And so the cyan section is the same across the red, the yellow, the blue, and so on, is the same across all of the family members. And we've identified those as sections. And then within each section, which can be more than one curve, we'll actually reflow that section. But the first step, and this is probably the most problematic step, is actually finding these sections and making the same sections across all of the family members. Okay, and then once you have the sections identified, we have a process of approximation that allows you to reflow the points and very closely approximate the curve. And again, these are quadratic Béziers, so you only have one control point per curve, and typically you want to do this at a minimum of 1,000 font units, preferably 2048. We would like to do it at a higher resolution than that. So our reflowing process, again, uses the mathematics of Bézier curves, and it's fairly involved. But basically what we do as a first step is we take the Bézier curve and we subdivide it recursively, and if you've ever written a rasterizer or something like that, you know how this is done. But we divide the curve up into a set of line segments that very closely approximate the curve, okay? And that's shown by these red and blue sections on the right-hand side there. And once we have those line sections, that gives us a set of tangents to the curve. And where those tangents intersect, which is shown up here on the left-hand side, those are potential places where we could put a control point. Okay? So we're going to take the original curve, which had its original control points, we're going to find these intersections, and then we're going to find the best intersection to give us the closest approximation to the curve. And the way in which we measure that goodness of fit is we actually take the two curves, which are now divided into line segments, and we measure the distance between the two curves, okay, totally as far from design as you can possibly get, but it's kind of fun for those of us that are mathematically oriented. But again, the whole point of doing this is to try to be as faithful to that design as possible, and to find a curve fit that really matches the original as best we can, given the constraints that the control point has to be on an integer. And again, I'm talking true type here, so the control point has to be on an integer font unit. Okay? So, harmony. Here's hopefully a good example of harmony. So we're going to change the outline through the interpolation process that is described in the OpenType spec. These are the gvar deltas that go together through that vector addition mechanism to actually change the control points. And the lines are showing you how the control point changes as you vary, in this case, the weight or the width axis. And now we're varying the width axis again. And you can sort of get a sense that there aren't too many control points, and that all of the control points they're changing, but they're changing in a fairly reasonable sort of way. Okay? So mathematically, it's nice and harmonious, but also in a design way, it's going to create intermediate interpolations that are pretty reasonable and pretty faithful to the intent of the design. The S glyph is also a very difficult one. It has what's called an inflection point. In some cases, it can have an extended inflection point. That's mathematically a little more complicated. But again, the algorithm is doing a very nice job of creating a harmonious set of points, not too many points, and we're changing those control points in a very reasonable sort of way. Okay? So, from my mathematical point of view, I just think that's a thing of beauty, right? It interpolates so well, and would you ever use one of those intermediate interpolations? Perhaps not. We have named instances within the font, but certainly if we're going to release a font out into the wild, we want to make sure that every intermediate interpolation is at least reasonable. Okay? And whether you use it or not is really another issue. But, fonts use math, but they're not ruled by it. So things can go wrong. So we have kinks, and we have twists, and we have simply bad ideas. So here's an example of a kink. Okay? So the default instance on the left-hand side, the control points are linear, and that's what that means is that the curve doesn't have a discontinuity in it, and it's nice and smooth. Okay? And then as you interpolate, okay, as we change one of the axes in this case, you see that a kink develops. That kink is not in the initial instance, and it's not in the final instance, but it shows up in the intermediate instances, okay? Again, that's not being faithful to the original design. This is not something we would want to release. And so, and occasionally, through various reasons, kinks do show up. And so here's another example of it. These are fun to look at, but there's an example. This was the original Avenir, where the kink shows up in that little corner of the 6. Oddly enough, it doesn't show up in the same corner in the 9, which has sort of flipped design, but that's mathematics for you, right? Okay, so what's happening here is, well, this is a problem in the algorithm. Here are the family members of the 6 along the bottom, and we've color-coded the sections. And you'll notice this orange section right here, okay? That orange section is consistent across all of the family members, but really what it does is it spans a little notch in some of the designs. Some of the designs have that little notch in them. Some of the designs don't have the notch, okay? And so the algorithm has incorrectly identified that that section is one entire section when it should have broken it up, okay? And that's the result. That results in that kink. So, so here's another example of a kink that shows up. And the reason, again, lack of harmony. In this case, as you see the B on the right-hand side, the bottom part of the B is nice and harmonious, not too many control points. All the control points move along a line in a fairly reasonable way. The top half of the B, however, is not harmonious. And in fact, the control points tend to slide along the tangent to the curve, and there's a lot of control points. The algorithm messed up, okay? And the reason it messed up was on the lower half of the B, it divided up the curve into two sections. The top half of the curve, it made one long section and tried to reflow that entire section. That's why you get more points, and that's why the interpolations take these strange paths, and in fact, it produces a kink. So one of the things we want to do is never release a font with a kink in it that wasn't intentional. Sometimes you have intentional kinks, and those are fine. So we've come up with a kink detector. This is part of automating our QA process, and so we start out for any line section that is linear. The control points are linear in the default font. We want them to stay linear as we go through the interpolation process. So we identify those linear sections in the default font, and then we divide up the interpolation space into increments of a tenth, arbitrarily, and then we look at whether or not they stay linear throughout that space. And this is actually a fairly good way of checking the entire variable design space to see that we haven't introduced any kinks. And of course, there's some technical details having to do with numerical accuracy and that sort of thing. In particular, if the original section was linear to within a certain amount, in other words, that angle between the one half of the section is small, in this case less than 2 degrees, again, somewhat arbitrary, we want the resulting section to also have a small angle between it, less than 8 degrees. Seems to work. And typically what causes a problem is if you have one leg is short and one leg is long, then that angle measurement is inaccurate. We get around that with some tricks, but so we're looking for this. We run this process fully automated, and then we produce a list of glyphs that the designer has to look at, or the QA person has to look at. And they go in and look at the interpolations and to see, is this a real kink or was this a false alarm? And usually, more often than not, it's a real kink, and it's a problem in the algorithm, and so we have to go back and fix that. This is the grotesque family, and it's actually a grotesque example of interpolation. This is sort of the equivalent of converting a coffee cup into a donut. Okay? And I know when variable fonts were first announced, a lot of people had nightmares that this was going to happen. We're not going to let this happen. So this is an example where you would have to go back and redesign the queue across all the family members to be more compatible. And that's a fair amount of work, and the question becomes, okay, that's work is cost. Are we going to do that for this family? that's a hard call. We haven't made that yet. Here's some more fun changes. This is kind of an example of a twist, and we also have an automated process to detect twists. Okay, there's actually a little twist in the outline there, and you can create a little tool to detect those twists. Here's another one. These are just so fun to look at. Here we're going from an upright style to an italic style, but it's really a different design. So we're actually kind of growing things out of the side and changing things. And the other thing you see is there's lots of points here. And a lot of these points were introduced, okay? And that's a sign of lack of harmony, right? Particularly when the normal weight doesn't have a lot of points, but the variable font does. That's a sign. And here's a good example of, this is kind of like growing a hand out of the side of your head. So we're going from an upright V to an italic V, and it's really just a different design sense. And so, so we've learned, okay? And one of the things we've learned is that combining styles is not always a good idea, right? At least in terms of intermediate interpolations. So combining upright and italic often gives us problems with the harmonization process, and often even when it does harmonize, and those examples were point compatible. Okay, the process said, hey, I worked, but you didn't really work. You messed up. But again, mathematically it worked. Design-wise, it didn't work. Okay, so let's not do this, right? So we've come up with an alternative approach that we kind of like. Is that if you actually need to combine an upright and an italic in one font, what you should do is actually take the regular style and have the variations within that. Take the italic style, append it to the regular, okay? It will vary across its family members nicely. And then use the G-sub mechanism for contextual substitution to actually switch between the upright and the italic. And here's an example in font view where we have an example where I'm going to vary the weight. It has a weight axis and an italic axis. And things will vary across the weight, but the italic will do a contextual substitution whenever I go beyond the midpoint of the axis. Okay, so I start out upright, I go across that middle of the italic axis. Now I can vary the weight axis. I can then look at changing the italic axis, and really it's a contextual change, a substitution. This, I think, is a much better approach if you need to combine uprights and italics, or any two things that have a really different style. If you absolutely have to have them in the same font, then the G-sub mechanism really allows you to switch between them. So, where are we now? Like I said, we've produced 25 variable fonts from binary legacy data as a test. We haven't released any of them. We're not announcing any product releases or business plans, but these are tests. The harmonization process works anywhere from 91% to 100%. And usually the 91% is when you're going from like the grotesque family, where you really shouldn't do that, or you're going from upright to italic. So we don't add a lot of points. Typically, for most font families, we're adding less than 5% additional points, so that's good. The variable font isn't going to have a lot more points in it. Sometimes we even reduce the number of points because the reflowing process will actually It just happens to find a set of control points that were less than the original. If you're going to harmonize uprights and italics in the same set, then that can add 10 to 20% more. That's another reason not to do that, okay? So, we found that the harmonization process is really a cost driver. Our current process is good, it's not perfect. We're working on a user-assisted process so that for that 5% or 2% or whatever it is, the font engineer will be able to go in, they'll be able to see what the problem was, step through the algorithm and say, oh, you misidentified a section, click on it and say, here's what the section should be split. It'll then run the process again, and hopefully it will run to completion, usually does. And then we're also automating our QA process to make sure we never deliver anything that has a bad interpolation. So, we can see the final production process. We're not there yet. You know, I don't know how many variable fonts we'll produce in a year, but you know, we will produce a fair number of them. That's our plan, at least. And then I think some of the issues that were raised here, I'm going to go a little bit off topic. Some of the issues that were raised here were, how do you use them, right? How do you control the use of variable fonts? And I think my own opinion is, you know, on the web, for example, if you download a web font that's a variable font, and you can use the JavaScript together with the CSS information, and it just needs a little bit more information about the font. You can either extract that directly from the font, or the WAF and the WAF2 mechanism has the ability to include metadata. So if we could come up with a standard extension to the metadata within the WAF and WAF2 format, I think that would really help the JavaScript and the user interfaces to know, okay, what axes do you have? And if it's one of the regular standard axes, I know what to do with it, but maybe you could give me some clues as to what to do with some of these additional axes. So I think there's hope for using variable fonts. We're certainly interested in producing them, and but it's not that easy. It's a fun technical problem, though, for those of us. So thank you very much.